Good morning, students. In the last lecture number 1 of Unit 4, MSc Final Environmental Chemistry, I have taught about hydrological cycle. Before hydrological cycle, we have studied about the water resources from where water can enter the cycle in the hydrogeological cycle. Now we will today study in lecture 2 the chemical composition of water bodies. About 80% of Earth's surface is covered by water. Water possesses abnormal physical properties compared to hydrogen sulfide, selenide and telluride. It is a liquid at room temperature with boiling point 100 degrees centigrade, melting point 0 degrees centigrade, density 1, high dielectric constant of 82, specific heat 1 calories per gram per degree centigrade, surface tension of 73 dynes per centimeter at 20 degrees centigrade, viscosity 0.01 poise at 20 degrees centigrade, dipole moment 1.84 into 10 to the power of minus 3 ESU, high heat of evaporation 540 calories per gram, molar heat of fusion 6.02 kilojoules. These properties of water are due to hydrogen bonding. Each water molecule is surrounded by 4 water molecule neighbors in tetrahedral manner. Classification of freshwater bodies. Fresh water constitute about 3% of global water resources. It may be of two natural types. Natural types. First has standing or lentic water or lentisca. Examples are lakes, ponds and swamps. Here circulation of water is slow and usually of vertical type. Second, a running or lotic water or lotus washed. Examples are rivers, streams and springs. Here circulation of water is fast and water moves horizontally. Now chemical composition, that is acid-base chemistry of lakes, rivers and streams. Lakes are freshwater bodies where the limnatic and profoundal zones are relatively large as compared to littoral zone. Rivers possesses a definite and continuous water current. Stream with its load of dissolved and suspended matter flows towards a lower line following the line of least resistance. Lakes, rivers, ponds and streams have slightly different chemical composition. Their common major anionic constituents are CO3 -2, SO4 -2 and silicate. The dominating cation is calcium ion +2, which is present as carbonate and bicarbonate. Calcium plays an important role in controlling the pH of aquatic environment. The average chemical composition, world mean, of river, stream and lake water is expressed in percentage weight as follows. Carbonate is 35.2, sulfate is 12.1, chloride is 5.7, nitrate is 0.9, calcium is 20.4, magnesium is 3.4, sodium is 5.8, potassium is 2.1, FeAl2O3 is 2.7 and SiO2 is 11.7. Some salts of calcium, phosphorus, nitrogen, silicon and other minerals are present in traces. Nitrate, nitrite and ammonium salts are essentially the food for aquatic vegetation. The growth of phytoplankton, blue-green algae, depend on nitrogen content of water. The concentration of salt in lake and river water is lower than that of seas. Thus, fresh water acts as a hypnotic medium for aquatic organisms. The pH of water is influenced by soluble organic and inorganic substances It is an intensity factor that measures the concentration of alkalinity or acidity present in water. The alkalinity is a capacity factor which is measure of the ability of water sample to sustain reaction with added acid or base. Lake water may be well buffered, transitional or acidic. Figure 2. In figure 2, we see that water in form of hydronium ion, that is water plus H ion, is well buffered in the pH range of 8.5. Then there is a transitional layer from 8.5 and 6.5. Then it goes alkaline above 4.5 pH, and then it is acidic below 2.5. Lake water status in terms of acid base nature. Lake water may be well buffered, transitional or acidic, depending on their position on the titration curve. The alkalinity is then a measure of extent of well buffered region. When a lake approaches the transitional stage, a very little acidification needed to drive it past the end point with its drop in pH. Such lakes are highly sensitive to acid inputs from natural or anthropogenic sources. A high value of alkalinity means that an excess of acid should be added to bring the lake into transitional and acidic range. Sensitivity of lake in terms of alkalinity is high when its proton accepting capacity is less than 200, or calcium carbonate is less than 10 and calcium ion 4. Moderate is when proton accepting tendency is from 200 to 400, calcium carbonate from 10 to 20, and calcium ion from 4 to 8. Similarly, sensitivity will be weak when it is more than 400, more than calcium carbonate more than 20, and calcium more than 8. The relationship between alkalinity expressed as proton accepting capacity and as calcium carbonate is expressed as 1 milligram calcium carbonate is equal to 1000 microgram of calcium carbonate. 1000 microgram divided by 100 gram mole is equal to 10 micromole carbonate. 100 gram per mole is molar mass of calcium carbonate. Since each carbonate ion can neutralize 2 hydronium ions, so 10 micromole carbonate ions is equivalent to 20 micron mole proton accepting tendency. Hence, alkalinity of a solution containing 20 micron mole per liter of proton accepting species could also be reported as 1 milligram per liter or calcium carbonate. Rivers and streams have a high percentage of oxygen than lakes. Oxygen content varies with seasonal and diurnal variations. Lakes showing winter stratification exhibit dilated oxygen concentration. CH4 and CO toxic gases are formed at the bottom due to decomposition of organic matter. Lakes and rivers that receive sewage and industrial effluent show an abundance of H2S as an anaerobic decomposition product. Ammonia is formed due to discharge of industrial waste into water. It is toxic to aquatic organisms in higher concentration. Thank you. This is second lecture, and we will study the third lecture with wetlands or wealth lands.